Hey everyone! In this video we're going to talk about graphs of basic functions, a little bit about relations, which I'll get into the difference between that and functions. Specifically we'll talk about continuity, some properties of functions, and then symmetry, and all of this is going to be looking at the graphs. So let's start with continuity, and continuity is just something being continuous. So mathematically, if something is continuous, it basically means that you're not going to pick up your pencil when you draw it. So if this is our XY coordinate system and we have a graph, then our graph could be continuous if I do something like this and I don't pick up my pen. Okay, so that's continuous. Now something that's not continuous, let's say I have this one. Okay, and it's probably exactly what you're envisioning. So I pick up my pen and I continue the graph elsewhere. So maybe it's up higher or somewhere else. And I can even do something like this, where part of the graph goes up and then the other half goes down, or the other part goes down. My graphs are not that perfect here, but the idea is that they're not continuous. So a couple of reasons why a graph would not be continuous. I'll show you some examples. So the first one here, this is a graph where there's a discontinuity, meaning it's not continuous, and it happens to be when x is 2. So this is a piecewise defined function where a piece of the function is like, let's say this one going down a little bit, and then another piece is up here, but this is still a function. Okay, so notice that there's an open point right here. So this point 2, 1, it doesn't actually exist on this first piece, but then this is a solid point right here. And so this part, let's say that's 2, 2, that one is filled in, so the graph actually does pass what's called the vertical line test for functions. If we draw a vertical line right here, we can see that this really just goes through that single point and then it's open right there. But this is a type of discontinuity. We would call this like a jump discontinuity, and this could be from a piecewise defined function. Over here, there's another type of discontinuity when a graph has a vertical asymptote. So the graph might approach infinity on one side and negative infinity on the other side of this asymptote, or both ends could go up toward the same infinity. But the point is that there's an asymptote where this x value, just chose 2 again, doesn't have a function value. So the function is like undefined. Sorry, that looks sloppy. Undefined for some reason when this x value equals to 2. So that does occur for some functions, and we would have discontinuity at those points. Another discontinuity might look very, very similar to this first one, but instead of it being a jump discontinuity, it looks more like just a hole in the graph. Something like this, where the graph is continuous, but then just at that single value it's not, and that would be a discontinuity as well. This one might occur if you have a function where you're able to like simplify the function. Let me give you an example. So say your function looks something like this, and it looks like the discontinuity would go away. So let's go with this one. So like x minus 3 times x plus 2, and then we're going to divide that by x minus 3. So this function, we could simplify this and it would look like we could get rid of the x minus 3 and just have x plus 2. However, originally this function x minus 3 was there in the denominator, meaning that 3, if we plug in 3, the function would be undefined, because remember, undefined occurs when you divide by 0. So if we divide by 0, the function will be undefined. So sometimes we get discontinuity because of something like this, where even though we could simplify, that value didn't, in this example 3, didn't actually work for the function. Alright, so that was a little bit about continuity. Next we're going to talk about some properties of functions. And there's quite a few properties, but we're going to focus on a few of them. We're going to be talking about whether a function increases, and we'll be able to tell that from the picture of the graph I'll give you a little bit of mathematical notation for how you could tell by plugging in values as well. If it's not increasing, maybe it's decreasing. And there's another possibility. If it's not increasing, if it's not decreasing, then it may be constant. So these are characteristics or properties of functions. And so if a graph is, or a function is increasing, visually it is going up toward the right. And just so you know, it doesn't have to increase over the whole graph. Sometimes the graph might go up for part of it and then down and then back up. So up toward the right is increasing. And mathematically, if we said that, okay, maybe we plug in two different x values and one x value is less than the next x value, basically saying if we plug in a bigger x, then we should get out a bigger y, because the graph goes right, which is bigger x's, then up also, so that's bigger y values. So this is saying mathematically with our notation that if our first x, let's switch this real quick, if our first x is smaller than our next x, or in other words our next x is larger than our first one, then our next y value should be larger than our first y value. Remember, f of x is just the same thing as y. So this is saying, if I go down here really quick, if I plug in one x value, let's say I plug in 1, and I get out a y value, let's say it's 2, then my next x value, if it's bigger, like let's say that I plug in 3, then my next y value should also be bigger. That's what increasing looks like. Notice this graph would go up toward the right. Decreasing is pretty much the opposite of this. So the decreasing graph goes down to the right. Okay, and again, it doesn't have to go down the whole time, but parts of functions are decreasing, like this one here. It would be decreasing on this portion between here and here, where it's going down toward the right in this area. Let's change colors right about here. So it would be decreasing on this interval. And our math notation for that, let's clear this up really quick. Our math notation would be very similar to this last reasoning, but kind of the opposite. If we plug in a bigger x value than our previous one, so if our x2 is bigger than our last x, than our x1, then our y value should actually get smaller. F of x1 is actually bigger than our next y value. Okay, so similar to my last drawing down here, if I plug in a bigger x value, let's say I plug in 1, I get out 2 again, but then my next x value is bigger, let's say 3, then this is saying that my y value is getting smaller. So maybe my y value here got smaller. It's a y value of 1. So the graph would be going down to the right. And then last, you can probably guess what this should look like. If it's not increasing, if it's not decreasing, then it's constant. So this should just look like a horizontal line. So it's constant if it's not going up or not going down. So no matter what happens with our inputs for our x values, so if our x values, we plug in x1, x2, x3, x4, and so on, any x value, our y value is not changing. And so we would have the same y value. Now, in terms of the slope of these functions, we could tell by the picture, or if we worked out some of these values, if the function was increasing, decreasing, or constant, what the slope is in terms of whether it's positive, negative, or 0. So think about this. If something is going up toward the right or getting larger, then the steepness or slope or rate of change is a positive one. So any increasing function has a positive slope or positive rate of change. And then if it's decreasing, well, exactly the opposite is happening. So we have a negative slope if the function is decreasing. And then you can guess it here. If the rate of change is not changing, or the slope is not changing, then the slope here would actually be 0. So slope equals 0 for any constant function or horizontal line. All right, let's take a look at an example and talk about how we will describe when a function is increasing, decreasing, or constant. So I'm just going to draw a graph of a random function that's going to be doing a number of different things. Okay, so let's say that our function looks like this, and then like this, and then it does something like this, and then it goes like that. Okay, and now I'm not going to label the y values because for talking about increasing, decreasing, or constant, we actually just need to know the x values because we talk about it in terms of the x coordinates and answer it. If the questions are about those three things, increasing, decreasing, or constant, we answer it with the x values. So in terms of increasing, I'm just going to say INC. The function is increasing on the intervals. If we kind of highlight it here, it's going up toward the right, starting here, going to about right there. Okay, so about right here, we have a point where the graph changes from going up and then down. So it goes from increasing to decreasing. It looks like it happens again. About my drawing is a little bit off from what I wanted to do, but it starts increasing again right about here and goes up toward the right until this moment. It stops going up, it just stays constant after that, but then it goes up again for the rest of this graph. Alright, so the way we would write when this function is increasing, we would say where does it start and stop for x values. So between x equals -3 is the starting point until x equals -2 is the stopping point. And so we would say that it starts increasing at -3 right here. Okay, I'll change the color here. Right here, it starts increasing here, and it increases until -2. And so we're just saying these two numbers. This is where it starts increasing, and this is where it stops increasing. And then it starts increasing again. Right here, let me label this. This would be 0. So it starts increasing again at 0. And then it stops increasing at 2. So we could say from here to here, from 0 until 2, it's increasing again. And then over here to the right, it's increasing from 4 all the way toward infinity. So increasing from 4 to infinity. So we would finish saying that this goes from 4 to infinity. Okay, so notice I did use brackets on -3, but parentheses on the other values. And brackets are just used when you can equal a value, and then we use parentheses if we cannot technically equal the value, the point. And so we do have a starting point on the graph here at -3. That's why I used a bracket. But then at -2, it's a little bit debatable. You could say that it's increasing at -2, or it's actually starting to decrease at -2. So I used a parenthesis, meaning that maybe we didn't quite want to say it's increasing at that number. Okay, so decreasing, this function, when is it going down toward the right? Well, it's going down toward the right on most of the other portions that we didn't already highlight in yellow, but a little bit is still constant. But it's going down toward the right here, right there. So that's between x is -2. Let's do it in green. X is -2 until x is 0. So from this x value to 0, the graph is going down toward the right. So that's how we would answer it. We would say from -2 until 0. And then the last part is just this last little piece over here where the function's not going up or down, it's staying constant. And so we would say that the function is constant on the interval from x is +2, excuse me, right here, from +2 until 4. So from 2 until 4. Okay, so now we're going to talk about whether functions are odd or even, which is also, there's a possibility of neither of these being the case. These are properties of functions, but they involve the symmetry. So we're going to be talking about symmetry now. And so if a function is odd, then mathematically or with our math notation, that's because if I plug a negative x into the function, I would get the same output or same y value as if I were to have a negative on the outside of the function value, like a negative applied to the outside. Basically, this is saying if I plug in a negative x, then I get a negative y, and I'll show you visually what that looks like. But even if I were to plug a negative value for x into the function, then I would get the same as if I were to plug in the positive x. And so these are what they look like mathematically for even and odd. But what's more interesting is the symmetry that we would get from graphs that had these properties. So if a function is odd, it has symmetry or is symmetric, and this is symmetric with respect to, I'm going to put WRT, with respect to, and this is the origin. So the origin, and so visually, what would that look like? So if I had a graph and it did something like this, that would be, and my drawing's not perfect, but that would be an example of an odd function, because here's the origin, it's like a mirror, and half of my graph would be on one part and it would mirror over to the other half. So what I mean by plugging in a negative x, if I were to put a negative, so let's say this part here, if I had an x here, and instead I plugged in the negative of that, so I plugged in a negative x, then what happened to my y value that corresponded to the first x, the positive one, that y value or f of x value, okay, that one here, the negative x actually put it down here and made it a negative y value. So we would get negative f of x. So that would be the symmetry about the origin. So if you need some numbers on here, if we had something like 1 and then 1, okay, so 1, 1 would be my point on this graph. If it's odd, if it has symmetry with respect to the origin, then the point negative 1, 1 would, negative 1, negative 1, excuse me, negative 1, negative 1 would also be a point on the graph. Okay, so if 1, 1 was a point on the graph, then negative 1, negative 1 would also be a point on the graph if it's odd. Now if it's even, this one also has symmetry, so this one is symmetric, and this time it's symmetric with respect to the y-axis. So even functions have symmetry with respect to the y-axis, and so visually this is saying if I plug in negative x, it's the same y value as if I were to have a positive x. So if the mirror is on the y-axis, so if you think of this as like being the mirror line right here, the y-axis, so if I have a point, let's say x here, x comma f of x, well, I get the same y value if I were to plug in a negative x over here. I get the same y value that I got from plugging in a positive x, and that's the symmetry across the y-axis, so that mirror line was there. Now there's actually also symmetry with respect to the x-axis, and so the thing with that one, so symmetry with respect to the x-axis, that one isn't considered even or odd as far as functions go, but this symmetry does exist, and an example of that is something like x is equal to y squared. And so this is an equation and it's not a function. So instead of this being a function, it's actually just a relation between x and y. It does fail the vertical line test, which would show us if a graph represents a function. If we look at these points that we plot for this, so let's say y is 1, 1 squared is 1. Okay, so if y is 1, x is 1. If y is negative 1, so if you square negative 1, you're going to get positive 1. So if y is negative 1, x is still positive 1. And similarly, let's say if y is 2, well, 2 squared would be 4. So when x is 4, y is 2. But also, if y is negative 2, if you square that, you're going to also get 4. So x is still 4 over here, but y is now negative 2. And so you get this sideways parabola. 0, 0 is also on this graph. And so this is a relation, this is a graph, but it's not a graph of a function. And it would fail the vertical line test, which says for any function, if you draw a vertical line, it can only touch your graph at most once. So this doesn't represent a function, however it is an equation and it does have symmetry. So this also does exist. Alright, so I want to show you an example of how to figure out if a function is odd or even based on the equation. If you have the graph, it's pretty clear. You can look for the symmetry. But if you don't have the graph, let's say for example you have something like a function f of x equals 6x cubed minus 9x. Well, we can use the facts that we learned about odd and even functions. So both involve plugging in a negative x into the function and seeing what that ends up becoming. So if I take my function and I put a negative x where there is an x, let's see what happens and how it compares to the original function. And that will tell us if the graph of this would be symmetric with respect to origin or y-axis. Alright, so right here, this is something negative multiplied 3 times, so that stays negative. Negative times a negative times a negative. So that becomes negative times 6, so negative 6x cubed. And then over here, this is a negative times a negative, which is positive. Okay, so that's our resulting function. Notice if we look back here, it is definitely not the same as the original. Okay, it does not look like the original exactly. We're off by some signs here. And so that means that this is not, since these are not equal, this is not going to be even. Because if you recall, even meant if I plugged in a negative x, it's the same output as if I plugged in a positive x. But now, remember what it meant to be odd. Odd said if I had a negative on the outside of the function, so if I had negative f of x, then it's the same as if I had a negative x plugged in. And if you take a look at that, look at your whole function that you started with, 6x cubed minus 9x. If you take that whole thing and apply a negative, notice what you get. You get exactly what's right above. You get a negative 6x cubed and a positive 9x. And so those are in fact the same. And so that means that this was an odd function. So an odd function, because f of negative x ended up equaling negative f of x. And then visually, if you were to graph this, it would have this shape to it. So it would look like this. Not a perfect drawing, but something like that. So it does have origin symmetry with respect to the origin, if you would mirror that. So like this piece would mirror through the origin over here, and then this piece would come through the origin like this and mirror down. And so there was symmetry visually there. Alright, so the last thing to talk about is the actual graphs of our basic functions. Here I have 8 functions for us. There are more functions that are considered like basic or parent functions, meaning that the other functions that you will come across come from these ones basically. But these are the ones that we're going to deal with most of the time. And so let's kind of go through some of them and talk about their parts. So the first one is the constant function. And notice visually that's just a horizontal line. So this is a function that no matter what x is, when you plug it in, you're going to get whatever y value this number equals. So c represents a constant number. So it could be like the number 3, and then no matter what x is, y is always 3. And for each of these, you would want to consider the domain and the range, the input and output. And so I'll just kind of write these off to the side here as we do it. But the domain for most of these will be all real numbers, because you can plug in any value for x and you'll get a real number output. And then the range does vary. So for this one here, the range is strictly just this constant value. It's just going to be c. And then the equation just looks like y equals, or f of x equals a number. And the next is the linear function, and this is just the identity one. So this particular picture is the identity function, because it's just simply y equals x. So the identity function is when y is equal to x, and that's what that picture is. But any linear function is just the graph of a line, and it can go up to the right or down to the right. So it could be increasing or decreasing. I mentioned earlier, these are basic or like parent functions, so other functions come from these. So a linear function, the line could look different. Like let's say it looks like this, the line could look like that, and it would have a different equation where there's more going on than just y equals to x. But it's still a linear function if it has the form y equals mx plus b, where m is the slope, so it's telling us how steep the line is, or the rate of change of that line, and then b would represent the y-intercept. So the domain and range for linear functions is all real numbers. So the domain is negative infinity to infinity, but so is the range. Then over here next is our absolute value function, which looks like a V shape. And this one, we can tell by the equation, it's the absolute value bars around x. So anything that would have been negative gets turned positive by the absolute value. So if we had y equal to absolute value of 3, that would be positive 3, so that's why we would get like 3 comma 3. But then if you put anything negative into this function, the absolute value bars turn it positive, so that would also be 3, positive 3, and then that's why we get this nice V shape. So the input for that, the domain, is all real numbers, but the output for this one, I'll say R for range. The range on this, because everything negative is getting turned positive, the range for this function starts at 0 and goes up to infinity. So we go from 0 to infinity. And then again, other functions can be derived from this, where you can shift or adjust where this V shape starts at, but for our basic function, it's going to start at 0, 0 and go upward. Then we have our quadratic function. So our quadratic function, we spend a lot of time with quadratic functions in algebra and calculus. But our quadratic function, this is the basic parent one, y equal to x squared. So y equal to x squared is our standard parabola that starts at 0, 0. And it has some key points that if you plug in 0, you get out 0. If you plug in 1, you get out 1. If you plug in negative 1, that gets squared and you get positive 1. And then usually it helps to know at least 2 more points. 2 squared gives you 4, and then negative 2 squared gives you negative 4, and that's how you form that parabola shape. And then in the future, we deal with these more, and there's more going on with the function as opposed to just y equals x squared. So for example, you might have something like y equals 2x squared minus 3x plus 7, and that is still a quadratic function. It's just there's more going on than just this basic quadratic function. So this one, it's very similar to absolute value in terms of its domain and range. The lowest y value is going to be 0 unless there's some shifting going on. Notice it's because anything negative got squared and turned positive, very similar to what happens with our graph of our absolute value function. So this has the same range as the absolute value graph. Alright, next is our square root function, and this one I kind of remember it like a shooting star shape, so it goes from 0, 0, because square root of 0 is 0, and it goes up toward the right like this and keeps going, and that's because we know square root of 1 is 1, square root, the next one we know that's a nice number, is square root of 4 is 2, and then we would say square root of 9 is 3. and that's where we get these values from. So 1, 1, 4, 2, and then slowly it goes up toward the right. And then notice we do not plug in anything negative here, because if we tried, if we said negative something, well then this starts to become imaginary, and then we can't see this on that graph. So this would actually be the imaginary number. If we plug in -1, and then the more negative numbers that we plug in, it would just continue to be imaginary. We get square root of 4 is 2, but the negative turns it imaginary, so 2i. And so this graph, the domain is not all real numbers. This one, we don't plug in anything negative into the square root, so the lowest number we plug in is 0. So 0 to infinity for the domain. And then the range is similar to the other ones that we just looked at. It goes from 0 upward. So the range being the y values, this graph goes up from 0 to infinity. Then the next one is our cubic function, that's x cubed. And this one looks sort of like a river shape. So it does have symmetry through the origin, similar to our example we did just a little bit ago. And we have some key points here. If you plug in -1, -1 cubed is -1, so that's why we're down here. Negative x gives us a negative y, and then +1 gives you 1, because 1 cubed is 1. And then let's just do another one. 2 to the 3rd power is 8, 2 cubed is 8, so it shoots up really fast and down really fast in those directions. So that's the cubic function. And this one does have symmetry about the origin. This is an odd function. So this one's odd. It's very much like our last one that we just tested whether it was odd or even. So it has symmetry with respect to the origin. And then we have the cube root function right next to it. So it's a little hard to see, but this is the cubed root. What number times itself 3 times equals what's inside of this symbol. So for example, cubed root of 8, what number times itself 3 times would give you 8, and it would be 2. So 2 times 2 times 2 would be 8. So if we input 8, like let's say that's 8, the output is 2. So if this is 8 for x, then y is 2. And so it's like a river shape, just like the cubic function or the cubing function, but it's turned sideways. This one also has symmetry about the origin, so this is also odd. And then lastly, we have what's called the reciprocal function, but more specifically, or more, I should say generally, it's a rational function. So rational functions have this behavior where they might have an asymptote, and at this one it has an asymptote at 0 because the function would be undefined. If you look at this denominator, if we plug in 0, this function's undefined, so that's why this graph actually has an asymptote at 0. And so these are our basic or parent functions. Most of the other functions you will come across are derived from these ones. They're basically a shift or a stretch of these ones. And we spend more time on just rational functions in general because there's a lot going on with them. But this one's domain is a little different because you cannot plug in the number that makes the whole thing undefined. So what I would say for this domain is I would say don't plug in 0. So you go from negative infinity, you jump over 0, and then you plug in numbers bigger than 0. So it's like you're skipping over 0 on the x-axis. So that would be the domain. And then the range on this one is actually the same as the domain. You don't actually ever equal 0. So that one's kind of an interesting one on itself. Alright, so these are some of our basic functions. You will see these over and over again and various forms of these. So they might get stretched out or get compressed, especially the quadratic functions. We'll see a lot of those that look like they got shifted, maybe down or over, or get wider or even flipped over. We do a lot with quadratic functions. Alright, we'll talk more about this later. Thanks for watching.